We finish off linear regression today. A lot of the questions are going to be from the homework because I want to kind of show you what their questions look like. And a lot of it has been covered before. And they just sometimes ask it in different ways. So I'm busily trying to hit the right button here, and I don't think I've hit it right yet. Okay, are you looking at chapter 3 regression lines? Is that what you can see? Okay, good, we're in the right place. So maybe make some of these ones a little bit bigger. Okay, now which one of the following could be the value of a correlation coefficient? Remember that R guy that we talked about. 0.14, yep, that could happen. Could 2.7 work? Could you get a correlation coefficient of 2.7? No. Correlation coefficients are only -1, which means it's a perfect line going downhill, or +1 going uphill. So that one would happen. 0 can happen. Isn't a correlation of 0 just a whole load of dots that are going nowhere? What about -1.2 then? Could you get a correlation coefficient of -1.2? I'll take a shake a head or a nod head if you don't want to talk. Okay, I see a shake head, so I agree. Now, remember that R squared is sometimes written as a proportion or a percent, right? So R squared, remember that guy called the coefficient of determination in some books, right? Can be written as a decimal or as a percentage. So if we go through these guys, some of these, but not all of them, right, could be the value of R squared. No, you'll never get a negative number from R squared because this is the R times R, right? That's how you calculate. Yes, you could get 0. Yes, you could get 0.3. And yes, you could get 1. Why can't you get 1.7? Why would that never happen?
It's not a square.
Well, you could get a number times itself that gives you 1.7, not necessarily for that reason. I mean, 1.5 times 1.5 would get you 2.25. It's to do with the size of it. Could R squared be bigger than 1?
No.
No, because R can only get to 1, so that makes that a no. Now, -50% is okay, and so is +25%. Because R squared, if you write it as a percentage, right? Why am I saying negative? Take that out, that's wrong. It could be +50% or +25%. It can't be negative and it can't be more than 100. So R squared takes values for 0. There's no fit at all, right? The data is just all over the place. Up to 100%, and an R squared of 100% is 100% fit. Remember we talked yesterday that R squared was another way of telling you how good the data was to being a straight line, right? So a 90% fit was really 90% of the time, all the dots were on the line or almost on the line, right? Whereas an R squared of 10% would be, 10% of the dots are close to the line, but the other 90% were miles off. So this question says, which one of the legitimate ones, that's these guys here, represents the strongest relationship? So in this list, which one of these, the ones that you can get, right, that are usable, is the best fit in the world? It's only one of them, which is actually a clue.
So correlation, the R can only go from -1 to 1.
Yep. And R squared can only go from 0 to 1 or 0 to 100% if you do percentages. So which one of them is the strongest?
25% to 1.
Yes. That's the answer. Just shrink this down a little bit.
A was wrong for me.
Did I hit something wrong with A? No, I think I'm okay.
He
with
did it backwards for A. You have to pick the ones that could not be the values. All the ones he picked were the ones
Oh.
that could be a value.
Now, do you
So,
know what the moral of
opposite.
that story is? Read the blinking question, isn't it? Yeah, fixed. Now, for 188 students, the correlation between the fastest speed that they'd ever driven and a random number that they chose between 1 and 10 is about 0, right? So the correlation coefficient R is close to 0. Describe what this indicates about the association. Doesn't that mean that the two variables are not connected, right? There's no connection, no association, right? R value. Pick a random number and what's the fastest you've ever been. I don't see why they two would ever have any connection. So you pick a sentence there that basically says that the scatter plot will have no visible path, right? Suppose the value of R squared is 100%. Now, isn't that a perfect fit, right? A perfect straight line. If R is 1, it's a perfect straight line. If R is -1, it's a perfect straight line. If R squared is just 1 or 100%, it's a perfect fit square, right? And perfect linear, right? Not a perfect curve, but a perfect straight line. And I'll let you figure that one out. Here's a good question. Nice short question. Suppose I had a linear relationship, right? A correlation coefficient, positive 0.2 or negative 0.6. Which of those two would be the stronger?
Negative point.
Agreed. When you talk about strength, we don't care if it's plus or minus. Doesn't plus just mean it's a fit going up the way and negative mean it's a fit going down the way? But isn't the 6, the 0.6, the important part as far as strength goes? Right. Now, here is, what is this? In this figure, we observe the correlation between left and right hands. Okay, you know, if you take your hand and you stretch it to the point where it's as good as it can go without hurting yourself, if you measure the distance from there to there, that's the hand spans, right? And your left hand and your right hand are probably not identical, but they should be darn close, right? You would expect. And if somebody's got a big left hand, would you expect them to have a big right hand? So there's definitely a positive thing going on. And here is what the data looks like for a whole load of people. And the correlation is positive 0.95. So far, so good. Now, they could ask you, what kind of strength is that? Wouldn't you say it was strong? Couldn't they also ask you, what is the value of R squared? Now, if they did do that, wouldn't you go to your calculator and you just type in 0.95 and you'd square it, and you get the answer 0.9025 if they wanted it as a proportion, or 90.25% if they wanted it as a percentage. But that's not what they're asking. They're asking you, which seems impossible, but it's not to answer, what would that correlation be if you measured the hand spans in inches? And the answer, maybe surprisingly enough, is 0.95. They don't care. It seems surprising that, but it doesn't matter what you measure things in. The correlation coefficient is a statistic, right? A number that you get that is unit free. It means it has no units. So if I measured your height in feet and your weight in kilograms, I get the same correlation coefficient than if I measured your height in centimeters and your weight in ounces. The correlation coefficient is the same number. That makes it very powerful because you can't distort it by choosing weird units to measure in. Oh, well, if you measure in inches, it looks better, right? or if you measure it in centigrade, it's better, right? That kind of, don't matter. Correlation coefficient is impervious to the units of measurement. That's a very powerful property.
I mean, I would say, I guess, unless of course you use like, it's a matter of the unit being not an accurate measurement or not, but that's a different thing, I guess.
Yeah, that's just error that you'd get in any measurement. And explain how you arrived at your answer. Well, you can figure out a sentence that makes sense to you. Now, here's a really very nice question. Here are 4 sets of data. And the first question is, which of those 4 represents the strongest linear relationship? So which of those 4 is closest? I see fingers on 2, would you agree? Which one of those would you say is the worst relationship? Now, I see 3, or maybe it's 4. What about 4? Do you think 3 or 4? Which one of them is worse? I'm going for 3. I could see 3 being hard, because wouldn't 3 be a straight line this way, a straight line this way, a straight line that way? Couldn't you do any straight line you want through that one? So that's a sign that it's a bad linear relationship. And now that I'm thinking about it, I'm going to agree with you. I was about to pick 4, but I'm looking at 4 and it's got a kind of vague, if you draw the sausage, it's kind of that way, not much, but enough to make a difference. Now, this one's going to be a little bit harder. I hope it's not too hard, because I want to be able to do it. Here we go. We have got 4, God, this is going to be tiny. We have got 4 pictures and correlations to go with each. Okay, one of those 4 pictures, I think I can do this one, is negative 0.9. Which one of those 4 pictures would get you a negative 0.9 correlation coefficient? If I'll tell you what, why don't I just make it a big picture and I'll tell you who the numbers are. Right. I see Cheyenne's got 2. I agree. Tell me why, Cheyenne.
It's the only one going down, going negative.
Seems a good answer. Agreed. I'll show you the choices. See them? Right. Now, what about from those 4 choices? 0, 0.3 and 0.6. 0.3 and 0.6. Okay, let's go for 0.6, although I'm not convinced there is a 0.6 here, but since that's my choice, which one of those 3 is 0.6? Yeah, would you agree that that's pushing it to be a 0.6? But if that's the only choice you're giving me, isn't that one better than the other 2? Right? So 0.6, 0.3, and the worst case scenario, 0. Right? 0.6, 0.3, although that's even pushing it, we agree, but evidently, if that's the only choices, that's the one I have to pick, and we're going with that one. Since that's the worst out of the set, that would be 4, and that's the end of these. Now, question 9, a data set on body temperature gives ages in years and body temperature in Fahrenheit for 100 blood donors aged 17 to 84. That's a lot of information. The data shows a correlation between the age of body temperature is negative 0.312. So age is the x-axis, body temperature is the y-axis. Since it's negative 0.312, doesn't that mean it's a downward sloping line? So the older you are, the colder your body temperature is. It might only be, 0.2 degrees, but it's colder, right? Which probably explains why old people are always feeling cold, right? Maybe that's the thing. So this value indicates that as the ages go up, the normal body temperature goes down. And that is oh, well, here's your choices. Forget the negative now, 0.312. From those 4 choices, what would you call a 0.312? which is about 9% if you did an R squared on it. Somewhat weak or somewhat strong. Very weak or very strong.
Somewhat strong.
I would say somewhat weak.
I would probably go somewhere weak. You want strong to be a 0.7, 8, 9, you know, 8 and 9 actually, if you want it to be strong. You want it to be moderate, you want it to be like, you know, 6, 7, 8 kind of number. And then you get to the weeks after that. Here are a whole load of questions in the similar kind of vein, so I'm not going to do that one. The correlation between the height and weight is 0.3 for 12 grade males. And wow, that's a big sample. Now, that's not a very good correlation coefficient, 0.3, because when you do it as a decimal, you get 0.09. Now, if they wanted this answer to be a percentage, wouldn't they put a little percentage symbol outside the box? So that's how I know they want the decimal. But as a decimal, and I like decimals, percentages better than decimal, isn't a 9% fit. It's easier to get, you know, what's going on here. Isn't that a very weak relationship? So evidently the height and the weight of 12th grade males is very unpredictable, right? Couldn't you get a 6-foot skinny beanpole guy and a 6-foot sumo wrestler guy, right? So for the same height, couldn't you have a huge variation in their weight? And can you have a small, you know, bodybuilder guy and a small beanpole guy, right? And the same thing is true at that end. So I guess that's what it's telling me. And now you see that the R squared is now down in that fit sentence. And it should be this one. 9% of the variation is explained, if I get the darn combination right. That. So a formal statement for what R squared is telling you is 9% of the variation, in this case in height, is explained by the other variable. I like just to say it's a 9% fit, because that's a very rudimentary way of phrasing it. And then it finishes with heights and weights were recorded in meters and kilograms, respectively. What would be the value if you decided to measure people in inches and pounds? Well, won't the answer be still 0.3? Units don't matter for correlation coefficients. Yeah, you can measure in feet or meters or pounds or kilograms, right? The X can be in meters and the Y's can be in kilograms. It won't matter. Your correlation coefficient is the same. Now, are they talking about the R value or are they talking about the R squared?
R.
They are. So that is the right answer. If they'd said, what would the value of R squared be? Wouldn't I just say, it's still 0.09, right? That wouldn't change either. Because isn't R squared just R times itself? Here's a little question that catches people out. It looks very simple. Calculate R squared. Well, if you go 0.11, oops, do my calculator, 0.11 square it. I'm looking at 0.0121. And then it says, which of these, or how do you interpret R squared? Right, the number of hours of sleep can be accurately predicted. The number of hours of sleep explains a proportion of their variation. The average hours of sleep cannot be accurately predicted, or the hours of study cannot explain the proportion. Would you agree an R squared of essentially 1% is there's no predictable values there? Wouldn't the data just look like a big bubble of nothing, right? If you see an R squared of essentially 1.21%. Doesn't that mean that only 1% of the time are you even going to be near whatever the straight line is? Isn't the other 99% of the time it's unpredictable? So the average number of hours sleep cannot be accurately predicted. That's why I chose that one. And here we have a whole load of data, and you're going to use SALT to find the correlation coefficient. Okay, let's see if this is
I
going
have
to...
a question about 12.
I just lost 12.
Oh, okay, it's fine.
I'll come back to it. Right. If the only thing you want from that data is the correlation coefficient, which of the top menus do I go to find out the value of R?
Regression.
When you click on it, it's going to ask you to select, oh darn, I should read the question. I believe it was latitude against August temperature. Let's just assume that it was. And if you click on that, you can even see the line. But there is your correlation coefficient. And there is your R squared. You see all the things that you need. And over here, isn't that the equation? So now I'm going to have to get back to our question. Oh, that was surprising. Ah, that's what I thought we'd done. Right, so you had the question, somebody asked about 12. Are we looking at 12 right now again? Right, what was the question? I can't hear you, Sharon. You hit the space bar.
Okay, so you said the answer was that the average number of hours cannot be accurately predicted.
Correct.
When I did it, the answer was hours of study explains this proportion of the observed variation in hours of sleep.
I like my answer better. But since you get 5 guesses, pick theirs.
Okay.
I think my answer is better. I'm arrogant enough to do that. Okay, so that was the one we just did a minute ago. I can't remember what the number was, but it was negative something, wasn't it? In fact, now that I look at it, shouldn't it have been January, not August that I picked? So the number won't even be the one I got. Oh, we did some stuff on outliers. This is what a homework question looks like. I will have to shrink this up a little bit because there are 4 pictures. Maybe one more. Now, sketch a scatter plot in which the correlation without an outlier is negative, but the correlation when the outlier is added is positive. So now we're going to have to look at some data. And it's going to be positive, negative when you use it, and positive when it's removed. Now that is a little bit of a awkwardness. So let's start at the beginning. So if you don't use the outlier, it's negative. Okay, so let's look at these pictures. If that outlier disappears, would you agree that this data is positive? If that outlier disappears, isn't the data still positive? If this outlier disappears, won't the data be negative? And this one disappears, won't the data be negative? So far, so good. So
That one's negative no matter what.
that one is negative no matter what, right? Now,
Yeah.
if you keep the outlier, you see that guy up there? If that outlier is far enough away from the data, and I would probably want to put it even higher than that, that outlier overwhelms the rest of the data. So what you would have got if you kept that outlier is actually that the line would point upwards. It would kind of go through the middle of the dots. Think of the outlier as like a big, strong magnet that's bending the line towards us. So if that outlier, I would exaggerate its position a bit more. Can you see that the line would be bent towards it, and so the data would be positive with it? But if it disappeared, it would be negative to start with. Right? So if we look at which of these is negative without the outlier, but is positive when you add it, it would be this picture here. If that outlier disappeared, isn't the data negative? If that outlier was being used, think of the magnet analogy, wouldn't the line be pulled at least towards it? Maybe not exactly on it, but at least towards it. And here's one that we kind of did. Remember square footage and price of the house, that kind of one? Here's a set of data with some square footage. If you look really carefully at that one, wouldn't that be an outlier? I mean, it's a huge house worth a lot of money. And up here, they tell you some of the numbers. The value, so this here is a place in California. The house with a square footage of that amount is definitely an outlier, which I agree with them. The value of R squared in this relationship was 82.5% when you used the outlier. Suppose the outlier disappears. What is the effect on the R squared value? So I'm going to try and show you what's going on here on the whiteboard. It's a very visual kind of situation. If you have a lot of data that's linear, and that data is, and you have a big outlier out here, the R and the R squared tend to be bigger than they really should be. You know, like a big number makes the mean bigger, right? And a big number makes the standard deviation bigger, right? We've seen that feature that outliers cause. Now, if you remove that outlier, the effect is that the R value will decrease. It will decrease to what it really should have been in the first place. And obviously R squared will decrease. So right now, the R squared is 82.5%, but that's with an outlier. If you removed the outlier, what would we be able to say? We might not be able to put a number on it, but wouldn't we say that it would decrease? And so there's a choice of 4 sentences there, 5 sentences there where you could basically get that one. Are we good? In fact, although they haven't done a question like this, and I hope they do, didn't I do one yesterday where if you wanted to check if something was an outlier, wouldn't you calculate the R or the R squared with it and then take it away and recalculate it? So different question, but can you imagine we got some data and the R value was 0.9 and it had an outlier in it, or I think it had an outlier. So I removed it and it became 0.71. Wouldn't that be evidence that the guy that I removed is an outlier? Right. If it was 0.9 and you removed it and it became 0.87, wouldn't that be evidence that it's not an outlier? Because when you remove a data, you're going to change the R value a little bit, no matter which one you remove. No real change. The number you removed is not an outlier. If you remove it and it's just one number, but it makes a big difference to the R value, you know you're looking at an outlier. Does that make sense? So let's move back to some more of these homework questions. So I say my goal today is to get this done. Just checking with them. Oh, I got this question. Here is the formula that you're already given. X is the putting distance, so that's there, putting distance, and Y is the percentage as a success rate. So, for instance, if you are 2 feet away, what is your success rate for this particular person? Well, it'd be 76.2. Take away 3.96 times 2. and go here, and I'll do that as a calculation. 76.2 take away 3.96 times 2 inches away. It's 68.28. Okay, suppose he was 20 feet away. Then it would be 76.2 times 3.96 times 20. Let's try that again. 76.2 take away 3.96 times 20. And the answer I get, and I'm glad they did this, is negative, why doesn't that appear? Click. There. Negative 3%. Would you agree 0% is the lowest percentage, which means you're never going to get it, right? Why is that second number? Different way of phrasing it. Remember yesterday I talked about interpolation and extrapolation, right? Like, don't try and guess the age of somebody who smokes 100 cigarettes a day because they end up living to their 10, right? That kind of situation. That's what's happening here, right? The model that they're using is only going to be used in this range, 5 to 15 feet. And as long as you use it in that range, you'll get numbers that are accurate and make sense. But if you try and do it for somebody plotting 20 feet away, do you see it's outside the range of the data? Outside extrapolation, right? XS, outside of. And that's what went wrong there. And then they get a little sentence here that you can talk about. And what's this? I should read this. Draw a graph of what you think the relationship between them is, right? So it's a number with a negative slope. So I would be looking at a number with a negative slope. Does that kind of make sense? It would probably look like that line there. The further away, the less you get. Is there any other straight lines in here? Not really. Okay. Okay, here is, they like this latitude, various places question, which is fine. So the following table gives the average temperature in August and the latitude of 20 cities in America. And it says, use this. I've got to show you this, I'm happy. Do you know that funny little hat? I think you were asking me yesterday, then, what did that thing look like? And can you see it there now? The tiny little hat. It should be there all the time, but at least they did it once, right? Just to show you that that's what it's like. So this here is the predicted Y, and Y is August temperature, right? So this is the predicted August temperature when the latitude is X. So if you find the latitude at the equator is 0, doesn't the answer come out as 113.6? Wouldn't we call that the y-intercept? And that makes sense. Could you imagine that on the equator, you could well be in a really hot place? I'm thinking the middle of Africa, right? The equator goes through there. Goes through the Amazon, I think, doesn't it? Equator? Well, it's close to the Amazon anyway. So that makes perfect sense. Should we use this equation? Well, yes and no. That's a bad answer, but here goes. Wasn't this data only collected in America? So wasn't the range of data only the latitudes from Alaska to Texas? And isn't the equator not in America? So aren't we actually doing extrapolation? And haven't we found them before that's a dangerous place to go? So if they use that argument, I would say no. If you use the argument, yes, it's outside the scope of the data, but it's reasonable to assume that that pattern is going to continue anyway, then wouldn't that be, yeah, 113.6 could be reasonable for the equator. My guess is, based on the previous question, that they're going to do no. I'll let you read that one. That's a fun one. I don't want to waste that one. Wish we could do that. Oh, we're almost finished. Here we go. Question 22. Researchers have found that there is a positive correlation between the average fat intake and the breast cancer rate across countries. So they go to Japan and they find out what's the average amount of fat that an adult in Japan eats and what percentage of them have breast cancer, right? Females typically, although actually males can get breast cancer, but it's less common. And they did it in Germany and they did it in America. You know, that like TV against life expectancy, right? And it's positive. So if you eat more fat, you also tend to have more breast cancer. I can understand that. Does this correlation prove that a high, that fat causes breast cancer, I guess, right? Can you remember my phrase? Correlation, right, does not mean causation. Couldn't it be that there is a lurking variable, some other cause? Make one up. Do you know if you eat a lot of fat, maybe you also eat a lot of calories and you also eat a lot of protein because you also eat a lot of stuff? Couldn't that just be a measure of how obese people are? And being obese could be a cause of breast cancer. So it's not necessarily the fat. In other words, if you cut out the entire fat intake, but they still ate too much of the other stuff, couldn't the breast cancer rate not change? In other words, the fat on its own isn't the problem, right? Now, it might be. What you have to do when you've got a good connection like that is that you have to try as best you can in an ethical way, see if you can collect data that shows that the fat intake is the real reason. So you'd have to find a country or countries that eat a lot of fat, but not much of anything else. And then find another country that eats a lot of fat and a lot of everything else. And if you could compare them and you find that they're the same, right, the cancer rate is the same, then wouldn't that mean, well, the only common feature is that they both eat lots of fat, right? And that might be a way of getting around that rather nasty problem of how do you decide if something is really causing something? You found an association, which is good, but you haven't found proof that something X causes Y. And so for the final question of this group, an observational study of 479 children found that children who slept with a nightlight or in a fully lit room before the age of 2 were more likely to be nearsighted than children who slept in darkness. I hope that's a made-up story, but let's just go with it. Does that mean that sleeping with a light on as an infant causes nearsightedness? And then they finish with, what is the most likely explanation? Okay, let's see what the choices are. Yes, since it's an observational study, that always establishes a causal connection. I would never say that answer to anything, right? Remember the TVs and life rate? Nah. No, there may be causation, but confounding variables, another name for a guy called a lurking variable, right? But there's a confounding factor that may be the cause, right? So that doesn't prove having a night light on when you're a baby makes you nearsightedness, but there might be another variable, right? A lurking, or as they call it here, a confounding variable. No, there is no causation because the observed association may be explained by how one or two other variables affect both the explanatory and the response variable. That's another no. And no, the response variable is causing a change in the explanatory variable. Well, forget that one. I'm not sure which of these two, because they both sound like they're saying the same thing, just differently. So I'm going to cheat and find out which one it is. Do you think it's the second one or the third one? You got a gut feeling? Let's find out. Oh, it was mine, the first one. So let's see what might be wrong with the sign. No, I like no. There is no causation because the observed association may be explained by one or two more variables affecting. You know, that is just another way of saying two. So I'm not quite sure why they picked two instead of the third dot, because I find it hard to, to see a difference. So almost finished. I've got a little story to tell you about connected to what we've just done here. But while I'm doing that.
Do we have enough time to go over 21, or can I come in the morning and ask about it?
Oh, God, no. Well, let's do 21. Yeah, I was going to do a story, but, well, 21's big. Well, I'll try to do 21. Put down your name while you're doing this, right? So you're not hanging about. So this is the obesity rate in 2014 versus the obesity rate in 1975 for 200 countries in the world. It's basically linear, not, kind of levels off there. So I would disagree. Does that not look more curvilinear to you than linear? But whatever, right? They've put a straight line through it, and it's definitely increased. Would you agree that in 1975, 20% of the people, that's what 0.2 is, were obese, and that's probably doubled up to 40% are now obese. That's not good. That dot there's probably America, by the way. Now, describe. Oh, we got the answers here. Describe the relationship. It appears to be positive and curvilinear. Oh, good. They agree with the curvilinear. Would it be appropriate to use? Well, if the data is curvilinear, it would not be appropriate to use. Why? Because it's curved, right? You shouldn't try to put straight line through data that's curved, right? The rightmost point, oh, it's not America. Do you know that guy that I said that's America? It's not. It's a place called Nauru. Nauru? Never heard of it. But it is a place northeast of Australia, right? It's way out in the Pacific on its own. Based on the scar plot, estimate the obesity rate in these two, right? The 75 and 2014. Someone told me a little click. If you click on the eye guy, can I do that? Oh, here we go. And can you see the two numbers that you need?
That's the part I was having trouble on.
Okay, so the little eye gets you, because if you don't do that, aren't you going to have a really hard time being accurate? So click on the eye and you can get the numbers you want. So I've lost the darn things, but evidently that's where these two numbers came from, right? Now it says, draw a line in the scar plot and show what data would look like if the obesity rate was the same in each country. Well, if the obesity rate was in the same country, wouldn't 0.1 go through 0.1 and 0.2 goes through 0.2? So one of these pictures should look like a nice straight line, and 0.2, 0.2, 0.3, there it is, it's that one. And every single one of those dots is above it, right? So if nothing changed, wouldn't all these dots be ziggy-zagging around this guy? But when you look at this, it's the same in 75 as it is in 2014. Everybody in the world has got bigger. So doesn't that mean that as a world trend, we're all getting fatter? And that's how they phrased that one. And there's the picture. Yeah. Although, if I know that's not America, because they told me it's not America. But if that's not America, won't that one there probably be America then? Because America has got a really high obesity rate, all right? You eat too much food. In my case, I'm not fat. I'm still going with, I'm just the wrong height.